All right, so here we have an example of some periodic motion with a spring that's been released, and the way that it goes up and down, it's going to repeat itself over and over again. It tells us that it rests 50 centimeters above a tabletop. The weight is pulled down 20 centimeters and released at time t equals 0. Okay, so from those first couple of sentences, we have a lot of really important information. So the weight rests 50 centimeters above a tabletop. So that's like your axis of curve. So I'm going to kind of draw like a dotted line at the 50 centimeter mark to give us our point of reference. Then it says at time t equals 0, it's pulled down 20 centimeters. So if the table's at 50 and you pull it down 20 centimeters, then you're going to end up at a value of 30. So at time t equals 0, we're at the 20 centimeter mark. Then it tells us that it takes 1.6 seconds for the weight to return to its starting position. So if you look at the scale along the bottom, we're going up by 0.2 each time. So then at 1.6, we have this point happening again. Now we want to fill in where the rest of the graph is occurring. So it was pulled down 20 centimeters, and when it's released, it's going to go up 20 centimeters above. The maximum value has to happen halfway between 0 and 1.6 because of the type of function that we're going to be using. So halfway between 0 and 1.6 is 0.8, so we need to go up to a value of 70. So from here, I have enough information to be able to draw my graph, and I can see that it's roughly like this. So that's one cycle. If I were to do a second cycle, I know that this bottom point right here has to repeat itself again after 1.6 seconds. So if I'm at 1.6 and I go another 1.6, we're going to be at 3.2. And then once again, if I'm at 1.8 at 70, that exact same point has to occur after another 1.6 seconds. So we'll be at 2.4. So it roughly looks like this. So that's how we can use that information to generate our graph. Then you're being asked to write the equation relating height to time, so your y-axis to your x-axis. Now, in order to get the equation, it's really important that we know what our amplitude is. And as stated in the lesson previous, the amplitude is always equal to the maximum value, which in this case is 70, minus the minimum value divided by 2. So our amplitude works out to give, sorry, this value right here should be 30, not 20. 40 divided by 2, which is 20. So we know our amplitude. That's the distance from the axis of curve, which is at 50, all the way to the maximum value or the minimum. And it's always a positive value in terms of magnitude. Our displacement, meaning where the axis of curve is located, is 70 plus 30 divided by 2, which equals 50. And that matches what we kind of already knew based on the equation. The next thing we need to know is what the value of k is. And k is based on the period and the value of 360, because the normal sine function without any transformations repeats after 360 degrees. So we have 360 degrees divided by, in this case, it told us that our period is 1.6, so k has a value of 225. Now I'm ready to write my equation. So I have y equals. Now this graph right here, the easiest function to use is cosine because it's simply a reflection. And whenever we have a reflection, we show that it's a reflection of the x-axis by including a negative. So I have negative 20 cosine of 225t plus 50. So this equation models what we have over here. There's no phase shift as such because it's much easier to simply reflect over the x-axis and have the negative cosine function. So these questions down here where it asks, what is the height of the weight after 2.8 seconds? Now that we have the equation, it's very easy to substitute in. So we have y equals negative 20 cosine of 225 multiplied by 2.8 plus 50. Make sure you multiply the 225 and 2.8 before you do the cosine. And when you do this, you should end up with a value of 50. Now, if we use our graph to check that answer, if we go to 2.8, does it look like it's right on the 50? Yes, it does. So we're in the right ballpark. Same exact process for part 2. So we're still using our equation. So 225 multiplied by 12.5 in this case, plus 50. So if I can't really use the graph for this one because our scale only goes up to a value of 4. So in this example, when you substitute in, you get about 42 meters. If you were to extend your graph, you would see that this in fact is the case. Now in part B, so it's slightly different. In question A, you were given the time looking for the height. In part B, you know the height and you're looking for the time. So if I go up to the graph and look at it, it says at what time will the height of the weight be 60 centimeters? So we're just going to assume that we're talking about one cycle at this point. So if I find 60 centimeters, I can tell there are two possible answers. So how are we going to come up with those answers? We're going to use the equation. So we have 60 equals negative 20 cosine of 225t plus 50. Now we're going to use our order of operations. So the first thing I'm going to do is subtract 50 from both sides. That leaves me with 10 equals negative 20 cosine of, oh, I just realized here I dropped the 5. So that's 225t. Our next step, you're going to divide both sides by negative 20 because our ultimate goal is to get t all alone. So I'm going to have negative 1/2 equals the cosine of 225t. We're trying to isolate the t. So now I'm going to move cos to the other side. Now cos, when it moves to the other side, we're going to do the inverse. So the cosine of negative 1 of negative 1/2 is equal to 225t. Using your calculator, if you do the inverse of cosine of negative 0.5, you're going to end up with 120 degrees would be your value, and then we'll drop the degrees in a second. So I've gotten rid of the cosine. Now I'm left with that 225. So I'm going to divide by 225, divide by 225. So when I do that, when I divide 120 by 225, we end up with about 0.53. Let's quickly have a look back up at our graph. So right here, it's somewhere between, so 0.2, 0.5. So my graph could be off a little bit, but it looks like it's in the realm. That's why we don't want to use the graph to answer that question, because it's not as accurate as it should be. Now, that's one of the answers. How are we going to come up with the other answer? That's where the idea of your quadrant comes into play. And we've looked at the idea throughout the course that oftentimes there are multiple answers when we're talking about trig. To go one full cycle, I need to go 1.6 seconds. So if I do one full rotation, that's 0.16 seconds. Now in this question, cosine is negative, so that's what we're trying to find over here. Cosine is negative in two quadrants. So we have this quadrant right here, and then we have this quadrant right here. So we found that 0.53 value. So this is 0.53, which means I must have 0.53 on this side. So therefore, the other time that you're going to have is going to be 0.53 plus, this is half, so it's half the rotation, plus 0.8, which would be 1.33 seconds. So this needs seconds as well. Now if we go back and look at that picture, does that make sense? Yes, it does, in terms of where our value should be. So that's how you can use your equation to get some answers in terms of solving, and it's all about making sure that you're following the appropriate order.